Hello, all. My name is Jordan Smith, um, senior at Southwestern University, and this is my my poster presentation over diagonalizing the undiagonalizable. I just want to say thank you for all that are watching. There's a lot of other things you can be doing right now, and so I appreciate you taking the time, to take a look at my presentation. Um, So we'll start off by giving a little bit of background. If you're taking a linear algebra class, you know about what it means for a matrix to be diagonalizable. So if not, we're going to go through it real quick so that you have kind of a bit of an understanding. If a matrix A is diagonalizable, we can break it down into PDP inverse, where P is just some invertible matrices, and D is a diagonal matrix with A's eigenvalues across the diagonal and zeros elsewhere. Um, the cool thing about doing this, if we can break up A into PDP inverse, if we're trying to find powers of A, we can just take our matrix D to the same power, multiply it by P and P inverse, and we get A to whatever power we're trying to find. And so it's a really cool thing that we can do, nifty trick that we all learn in linear algebra. But the question that then arises from that is, what then do we do to find powers of matrices that aren't diagonalizable? We call those matrices defective. Um, so how do we easily find powers of A if A is defective? That's kind of the question that we're working with in this whole project, this research project. So I'm going to talk about something that's not really mentioned in linear algebra. It's something called a Jordan form. Um, it's important to know that every n by n matrix A can be written as SJS inverse, like PDP inverse, where S is invertible. And S actually, in this case, contains A's generalized eigenvectors, uh, and J is the Jordan form of A. So what is a Jordan matrix? So Jordan matrix, here's an example of a 3 by 3 Jordan block matrix. So all it is uh, if matrix A has some eigenvalue, its eigenvalues will go across the diagonal and we'll have ones across the upper subdiagonal. And then zeros will be elsewhere in the matrix. Um, and so a Jordan matrix can consist of multiple Jordan blocks, J1, J2, J3, where the eigenvalue for J1 is lambda 1, and then eigenvalue for J2 is lambda 2, and so on and so forth. So a Jordan matrix can consist of one block, multiple blocks, 10 blocks, 15 blocks. It just depends on the matrix A that you're dealing with. If matrix A is diagonalizable, our Jordan matrix will equal our diagonal matrix from earlier. So basically, the Jordan form will look like multiple singleton blocks, like here, just going across diagonal with no ones, just a whole bunch of zeros surrounding it. So it equals our diagonal matrix D. If A is defective, we know that at least one Jordan block of size greater than 1 exists. So there can be singleton blocks, but we know that there will have to be at least one Jordan block of size greater than 1. So it is, obviously I have to say that trying to figure out the Jordan form of a matrix is very computationally difficult to find, but if we know what the Jordan form looks like, it can be very useful in this process. And so our theorem for this project is you can lift an undiagonalizable matrix A with n minus 1 generalized eigenvectors for every Jordan block of A so that it is diagonalizable and powers of A are easily extracted. So what is this lifting that we're talking about here? So you can essentially lift any matrix A into like a higher dimension by just setting it inside of a larger matrix, A prime. And so our matrix A will just be placed in this bottom right corner, and then values will be placed around it. If you just choose random values to be placed around our matrix A, it's important to note that the eigensystem of A prime will just be completely messed up and it will look nothing like A. However, if we choose um, our alpha or V and a W star to be specific values, we can, if we choose alpha, V, and W star as such below, where alpha is lambda plus 1 across the diagonal and negative 1 across the lower subdiagonal, V is all of A's generalized eigenvectors, and then W star is all of A's left generalized eigenvectors. Uh, we know that A prime is then diagonalizable, which is what we want. The eigenvalues of A are also the eigenvalues of A prime. All other eigenvalues of A prime can then be predictable. And then, like in the theorem, we can easily extract powers of A from A prime, which is kind of the whole goal of this. Find powers of A if it's defective. And so we can do that if we choose specific values to go around our matrix A. So we're going to look at an example. So here's our matrix A. Made this extremely messy, so he proved to you that this actually works. The Jordan form of the matrix A is just a single 3x3 Jordan block. Its eigenvalue, the eigenvalue of A is going to be 4. And so our alpha is chosen to be lambda plus 1 across the diagonal. V, right eigenvectors, W star, left eigenvectors. And so we just throw all this bad boy in here to create our A prime. And so we're going to take A prime to the 8th power. And you get this really beautiful matrix. And so how in the world do we extract powers of A from this mess of A prime to the 8th? And so if you look at this top right corner, the top right corner of the poster, we developed this formula where we can take this bottom right submatrix in red, which will be the size of your matrix A, regardless of how big of it is, wherever your matrix A is. You're going to take this bottom right submatrix after you've taken powers of A prime, and you're going to subtract off V times this summation times W star. And so everything within the summation, we know what alpha is. We know what our lambda value is, and then L is just going to be our alpha matrix minus lambda plus 1 across the diagonal. And so we know all of these things. And so when we take this formula and look at it for our specific example, L is alpha minus lambda plus 1 across the diagonal. We can plug in all these values. We know V, know W star, we know all these. And so we can take this bottom right submatrix, subtract this off, and our algorithm spits out this result for our matrix A to the 8th power. And so you might want to get on Mathematica and check me on this, but if you just start with our matrix A up here and don't do this process and take it to the 8th power, you will get the exact same result. And so we've accomplished our goal. You might also want to look at A prime and see if the eigenvalues of A are still within A prime. But I'm here to tell you that they are. If you want to check me, you can. So we know that this works for a few cases. If we know that the Jordan form of A has only one block, like in our example here, it is straightforward to eigenlift, and there exists a formula that allows us to easily extract powers of A from A prime, which is what we just did. Another case, if we know that each eigenvalue of A has a geometric multiplicity of 1, meaning A is non-derogatory, it is still easy to eigenlift, but formulas to extract powers of A become more complicated. So what that means, if we have a matrix that has a Jordan form that looks kind of like this, this works if we know that lambda 1 is not equal to lambda 3 and lambda 2 is not equal to lambda 1. So all eigenvalues in different blocks have to be different. Because a Jordan form is sometimes difficult to find, we can see that an eigenvalue has a geometric multiplicity of 2, but we don't, like, it's hard to tell whether or not that pops up in, 2 singletons or, 2 2x2s. And so because it's computationally difficult to find, we don't yet know how to make this process work if A is non-derogatory, if it's not non-derogatory. Um, so of course, future work, we want to expand on our formula to work with all non-diagonalizable matrices. Obviously, that's the goal. And then we want to find a general process of eigenlifting that does not depend on knowing the Jordan form beforehand. And so I just want to thank Dr. F, who's the mentor for this research project, Aaron Waslazik and Sarah Friday, who are my research buddies and have put in just as much as work as I have into this project, Southwestern University, and then Scope Summer Research Program for funding this research. Thank you very much, and that is my presentation.